Alright everybody, we're kind of putting everything together here for electric circuits, for circuits that are just composed of power sources and resistors anyway. So this is a pretty big process of finding voltage and current and power for any resistor in this network of parallel and series resistors with just a single battery or other power supply. I hope you'll forgive my voice, and if I start coughing here, I hope you forgive that. Get a little bit of a sinus infection as I'm recording this, and if you don't forgive it, then we're not friends anymore. We're not. Well, that aside, we have a few equations we're going to be using consistently throughout this process. Ohm's law is the first one. V equals IR, voltage equals current times resistance. Gets a lot of use. We're going to be adding resistors together, so if they're in series, we'll use this equation. If they're in parallel, we'll use this one. And then if we're looking for the power dissipated for any resistor, we've got three different forms of that. The current times the voltage squared times the resistance, or the current squared divided by the resistance are all equal to power. So I've sketched out a diagram for a circuit that we can try this on. Let's just find everything for this. So we've got all the resistances. Let's do the voltage drop across each resistor, the current through each resistor, and the power for each resistor. And let's even do some kind of fancy color coding business here. Let's say for blue we'll do current, so we'll have maybe I total would be a good thing to record, and then I1, and I2, and I3, and I4, and voltage, I picked green, so V total, and V1, and V2, and V3, and V4, and V5, just 4. Okay, and then we'll do red for power, or let's do red. Pink's a little tough to see. Okay, total power, and then P1, and P2, and P3, and P4. Okay, lots of things that we're going to be solving for here. So let's worry about those totals first. So total voltage, actually, we can do right now. We have a battery that's 5 volts, so for all of these put together in the arrangement that we have, we must have a total voltage drop of 5 volts. It goes up by 5, and then as it goes around, it goes down by 5. So this is a 5-volt drop overall. So any path that I take to get around this circuit should have a total of 5 volts. So I know that the voltage drop across 1 plus, say, the voltage drop across 4 has to be 5 volts. And the voltage drop across 1 plus across 2 plus across 3, that has to be 5 volts as well. So either path that I take, we have to have a total voltage of 5 volts. Total current, don't know. But I know total voltage. If I knew total resistance or equivalent resistance, well, then I could find total current. So that's going to be our first step then, is identifying what the total resistance is, or what the equivalent resistance is for this entire circuit. Once we know that, we can figure out the overall current, and then we can see how that starts to break up into little pieces. So, I made another sketch, or I made a copy of this that we can work on for total resistance. So, remember, the general process here is we combine resistors and redraw as we go. So we need to find resistors that are either just in series or just in parallel. And so I see that R2 and R3, those are just in series. And so for series circuits, we just add the values together. So these two have an equivalent resistance of 40 ohms. So let's redraw it like that. So that now is 40 ohms. Okay, now I see these two are in parallel. There's no combinations there. So to get the total or the equivalent resistance there, I'm going to say that 1 over the total, or another notation that's useful for this is the total resistance inverse is equal to 40 inverse. That should be 40 ohms. So the inverse of 40 ohms plus let me fix this up a little bit. There we go. Inverse of 40 ohms plus the inverse of 30 ohms. And so if I want just R by itself, I'll take the inverse of both sides like this. Whoops, I made that a square instead of an inverse. There we go. Okay, so that's something that you can plug into your calculator all in one step, so save you a little bit of time. So 40 inverse plus 30, the inverse of that, and take the inverse of the sum. For this we get a total resistance of 17.1 ohms. So we'll erase these two. Okay, and replace that with a single resistor whose value is 17.1 ohms. Alright, and then I have just these two in series with each other, so we'll add those together. Gives us 27.1 ohms. Just redraw that quick. Okay. 27.1 ohms. There we go. So if we know that the voltage across the entire circuit is 5 volts and the equivalent resistance is 27.1 ohms, then I can use V equals IR, where V is 5 volts, and times I times my resistance, which is 27.1 ohms. And divide both sides by 27.1. Oops. And we get our current of 0.185 amps. Alright, back to here. Current total is 0.185 amps. Okay, so leaving the battery, we have 0.185 amps, and coming back into the battery, we have 0.185 amps, and then that 0.185, that extends until we have a break where we have a split in our circuit, so right up until this point. So R1 is 0.15 amps. Alright, now for the first resistor, now we know the current and we know the resistance, so we can figure out the voltage on that guy. So the voltage drop of that R1 value must be V equals IR. So V1 is going to be equal to 0.185 amps times the resistance, which is 10 ohms. And we get 1.85 volts. Alright, and actually we can go a little bit further with voltage here. We said that we know for any path that the current can follow here, our total voltage drop has to be 5 volts. So if we traced a path along like this, so it goes just through R1 and R4, then R1 and R4, they're the only two resistors to provide that voltage drop. So if R1 drops it by 1.85 volts, then R4 must pick up the rest of the 5, so that would be 3.15 volts. Some people find it useful to make a note as they go through here of what the voltage or what the electric potential at each point along the way would be. So we just say that the negative end of the battery, we'll call that a 0, and then we'll call this 5 volts. And then over here we dropped by 1.85, so that left us with, so this is 5 volts. So this is 3.85 volts. 3.85 volts still here, and this has to be 0 volts. So across this one resistor, we have to drop by 3. Oops, I miswrote that. 3.15, not 85. 3.15 volts. Okay, so then we know that R2 and R3, they have to have a total voltage drop of 3.15 volts as well. So we can figure out how much current and how much voltage drop they each have as our next step. All right. Now, if we look at at R4, we have both the value for the resistance and the value for the voltage across R4, so we can figure out how much current R4 takes as well. So you see this pattern here? We just keep going into Ohm's law here. Whoops, Ohm's law with different setups. As we get to know more and more about our circuit, we can do more and more with Ohm's law. So I4 times R4. And so we're looking for I4 here. We've got V4 is 3.15 volts is equal to I4 times the resistance, which is 30 ohms. Okay, and so I4 then has to be 3.15 divided by 30, gives us 0.105 amps. Okay, 0.105 amps going through this direction. But wait a minute. A minute ago we said we had an amperage or a current of 0.185. How come now it's 0.105? Well, we had this split here. Some of it goes down this path and some goes down this path. So if 0.105 goes down this path, that must mean we have 0.8 left over to go down through this path. 0.8 amps. So that's through 2 and through 3, so we can fill that in. 0.08 amps. 0.08 amps. There we go. Okay, so we know the currents for all of them. It's good. Now voltages, well, for 2 and for 3, we have both the resistance and current, so we can figure those out next. Go back to green for voltage. We'll say V2 is equal to I2 times R2. So V2 is equal to, what do we say, 0.08 amps for I2. And R2 is 20 ohms. Okay, and so we get V2 is equal to I guess it'd be, let's see, 1.6 volts there. Okay, and then another one for R3, and R3 has the same value. So V3 is going to be equal to I3 times R3. So it's still 20 ohms, still the 0.08 amps. So this one is going to be exactly the same, 1.6 volts. Okay, and we said that whichever path you took here, we had to have the same voltage drop from 3.15 down to 0. So we either go here, and this one has a voltage drop of 3.15. These ones, we got 1.6 for each of them, so that looks like a little rounding error there. So that actually adds up to 3.2 instead of 3.15, but you know, we're darn close there, so that's not a real big deal on these ones. So that's all our voltages and currents just by using Ohm's law again and again, and knowing that our current has to be conserved. We can't lose total current or gain total current, so we have to have the same amount going into this spot as we do leaving that spot. We'll talk more about that later on. It's called one of Kirchhoff's rules. Last bit here is to find power. So the power total, let's see, back over to here, We know that our voltage is 5 volts, our overall resistance is 27.1, so if we want to find the total power, remember the total power, or the power equation, there's a few different variations here. We know voltage and resistance. We actually know current also, but just voltage and resistance shown on that diagram. So V squared times R. And our voltage here was 5 volts. And our resistance is 27.1 ohms. And so the overall power is going to be 5 squared is 25 times 27.1 gives us 678 watts. So that's the total. Okay, and then another form of that equation that we can use here is current times voltage. So if we just look at each of these currents and multiply by the voltages, we should be able to get the powers pretty quick. So for the first one, we have 0.185 times 1.85 gives us 0.34 watts. Alright, the second one, we've got 0.08 times 1.6 gives us 0.128. And for the third one, we've got 0.08 amps times 1.6 volts. Oops, I just did that one. Same as the last one we just did, so that's still 0.128 watts. And then our fourth one is 0.105 times 3.15, which gives us 0.33 watts. Okay, and looking at the numbers that we got here, that power total, that seems a little bit off. So let's see if we can figure out something that went wrong here. It's V squared times R. It's supposed to be V squared over R. Did I miswrite that? IV, let's see if we replace that. Yeah, I had that backwards, don't I? It's V squared over R. Whoops. Here we go. R or I squared times R. Yeah. Yep, that's it. Okay. So back here, V squared over R. Okay, so 25 over 27.1. There we go. And so instead of that gigantic number, 27.1, there we go, we get a much more reasonable 0.923 watts. Okay, so replace that there. And you'll notice here that we get about 0.3 plus about 0.3 is 0.6, a little more than that, plus 0.128 plus 0.128, we're at about 0.9. So if you take all these powers and you add them up, you should get the total power, which is when I realized that something was messed up there. We didn't have something that made sense there. So that's what we're looking at doing on all of these problems, is just breaking up the problem into a series of little tiny steps, finding the individual currents and voltages and powers using Ohm's law, using the idea that charge is conserved, that there's no potential difference between 2 points on a conductor. And that's important. So all those things combine, and it's not a real difficult math process, but they can be lengthy and complicated circuits to deal with. So be sure and get some practice on these.